This is really straight to full class to teaching, half Zoom and half in person. So I'm excited to actually teach again and pretty much everybody in person again. So welcome. I'm Professor Rasmussen, Angela Rasmussen. I've been here like 20 years, so been here a long time teaching. Love to teach. This is my first time teaching 2240 though. So bear with me, there's not as many resources for them. And so it's going to be a little bit slow getting all the resources that I usually have for some of my other classes going. So as you saw, like last night, I finally got this published as far as the beginning of the Canvas course. So I want to kind of go through a little bit of what I expect. So let's see. So on the syllabus, you're going to see the outline of, you know, all of the requirements that I will be expecting. The majority of the grading is going to be from exams. So there's going to be 3 exams. For the final, I give an optional final where you can retake any of the exams that you want. I will let you take up to all 3 of them. So you can do a direct replacement if you want, so that if you don't do as well throughout, but want to do really well by the end, you'll have that opportunity. So because of that, it will be during the normal final time, but if you want to take more than just the 1 final or 2, you'll need to just kind of arrange with me another time to have that proctored. So all the exams do need to be proctored. We will be meeting in the Ingman lab to take the exams on exam day. So I'll be reserving that. And then we're going to take them on Canvas. So do bring a phone or a way to scan, or you can use the scanner in the CADE lab where you'll write out your work and then upload that for partial credit for the exams. So do come prepared for that. Let's see what else. The other things you're going to have is some assignments. The assignments will be kind of like discussions, and then you're going to have assessments, which are going to be kind of like your homework, and then you're going to have a quiz pretty much each week. And so those will be ways to be able to self-assess, like how am I doing? Do I understand this material? What am I missing? So that you can be prepared for the exam that will be coming up. Out of those, I know life happens. So for the assignments, I dropped the lowest 3 scores in those. So if you have situations you're not able to do them, you can drop the lowest 3 scores. For the assessments, you get to drop the lowest 2 scores. For the assessments, there's something you can redo. So as you're doing them, if you aren't successful the first time and you only get 10 points out of 40, you can redo them again, and you can do it up to 3 times. So typically it's a way again of saying like, do I know this material or not? So do those other examples before you start it, so that hopefully it will just be a one-time attempt to say, yeah, I do understand this material now, but if not, you at least will be able to see what kind of a problem it's asking, go figure out what to do, and then go back to it and say, okay, now let me reattempt a different one. It will cycle through several different problems, so it may not be the same problem you just had. So it will be a new problem. So there's like a bank of problems, which is what I mean by I don't have all that material up there yet. Then the quizzes, I will drop the lowest score on the quiz. So you get to drop your lowest one. Quizzes is going to be on your own time. It will be typically on a Tuesday, except for on the Labor Day, we're going to have it on the Wednesday, just because the Monday we're not here. So it will open up that morning at 8 a.m. on Tuesday, and you'll have till, I think it's like 10 p.m. or maybe even midnight that day. So sometime that day, you just need to take the quiz. All right. Any questions about kind of what the evaluation is going to be in here? Okay. All right. As far as the schedule, maybe. Okay, it's on that page, but for some reason it's not connecting so well. So on this, it has the dates of the week that we have lecture, a tentative topics that we're going to be discussing, and then over on the text reading is going to be from the Eulaby book. So this is the same book from 1240 that you guys have access to. And I'll show you in a second where the link is if you don't remember where it is. And so do read those chapters. This is first part is going to be the review. So 1 through 5 was what you focused on in 1240. And so then we're going to do a quick review. Actually, I'm not going to do a ton of review today. It's going to be throughout. We're going to do the review. And we're already going to start reviewing on the capacitors and inductors is where we're going to start. And then the assignments that will kind of be coming up is listed on there. So you can see for this next Monday, there's going to be a tell me about yourself assignment, a assessment for the RC circuits, an assessment for the RL circuits, and then you'll have that quiz next Tuesday or that will be next Wednesday. So we won't have anything we won't have anything that's coming up except for, oh, that was supposed to be, that is a wrong date. That is the August 30th. So that will be this Thursday or Tuesday. Hold up yet. Okay, I'll correct that. So that quiz will be this next coming up Tuesday. I just saw that was an error. And so that will outline for the semester when the assignments are due. So hopefully that helps you guys understand when is something due and when you can do that. Okay, any questions? Yes.
I just want to ask, what are the assessments?
So it's like a quiz, except for you can just redo them. So it will be on Canvas. And it's, yeah, it's at home. It's kind of like what I view as homework. So I'm not going to do actual, like do these 20 problems. They're going to be there that you can kind of look through past problems, learn on how to do them yourselves. And then the assessment is to help you say, do I understand that? So I'm only going to do like 2 problems.
Right.
And then you'll have the quiz to then, after you do those, that will help you say, am I ready for the quiz? And then you can take the quiz. The quiz will be only a 1 attempt.
Okay.
Where the assessment, if you aren't successful, like I said, it will be like 1 problem. So if you're not successful on it, you can just redo it up to 3 times.
Perfect.
So you can get up to 100%. Any other questions or clarifications? Yes.
Our first quiz is next.
Correct. Yeah. So sorry, that is an error on that date and I will correct it and get it posted again. But yes, it will be on RC and RL, which we're going to actually start today talking about. And I'll tell you a little bit about my style. So it's going to be a flipped classroom. So there'll actually be material later today that will be like all of the material you can go and watch. So there'll be a lot of information to go back and review on if you've forgotten some things. And there'll be like videos you can go and watch and help support yourself. And then there'll be some videos to watch for Wednesday to help be more prepared. And then in here, we're going to do discussions, like any questions you've had about anything you've watched. And then we're going to do problems also in here. So we'll work in small groups that you guys can see, am I really getting the technique of what I want to understand out of this? And I do tend to like overwhelm students with a lot of information. So do know like, okay, at first it will feel really overwhelming, but we'll go through problem and problem and problem till it really feels like, okay, I am starting to understand this now. So that's kind of my style. So don't give up. Do know that you might feel overwhelmed at first with the beginning of the material, but then as we work more and more through it, you'll be prepared by the exam time. If you still spend a lot of time and effort on it. I try to make it so everybody in here can be successful and everybody can earn an A. You just have to put in the effort and the time and energy for that. Okay. All right. Any other questions?
Yeah.
Yes.
Your quizzes, are they on campus as well? or
Yep.
are they in person?
Yep. They'll be on Canvas. So they'll be on a Tuesday in between our Monday and Wednesday class. So anytime Tuesday day and night, you can take that quiz. Any other clarifications, questions? So I had mentioned the book link on the syllabus. Let's see, is it on the syllabus? Required materials, there it is. So under required materials, if you just click on the textbook link, it will bring you to this page. Maybe, I don't think I'm getting very good internet. There we go. Scroll down on here and there's the ULB book. Just fill out the form that it asks you for once you do the free download. So it is a free downloadable book. And so just be able to utilize that. And then all of the reading refers to that version. Amy, do you want to say anything about 2245? Yeah, if you want to go ahead. So Amy Verkler is another faculty. She's going to be helping out with the lab. And so for 2245, I'll let you just.
Yeah,
express.
so when doing the lab portion, it will run fairly independently of this class. We tried to line things up somewhat. So if you have questions about lab, come see me. If you need to be moved into a different lab section, come see me. We just learned the other day that some of the lab sections were limited to 14 students for some reason. So they still have space if you need to move. Yeah,
So, and we're not requiring 82s in Discovery?
we are not.
Okay, so if you want to use the 82, you can still use the 82, or if you even have an older MyDAC, you're welcome to use those. Those are going to be very helpful to use at home if you want to still work on the lab material at home.
So yeah, there's one lab section that's virtual and they will need 82s.
Oh, yeah, that's true. Oh, so there was a posting of one of.
Yeah, so the lab section 1 is virtual.
Okay, so if you are in lab section 1, do come at any point to get help at any of the other lab section times to get help from TA. So that means.
But your TA will still be on Zoom with you. So you'll still have a TA assigned who will be around during your assigned lab time.
But it is very difficult if, as you guys probably already know, because you probably attempted some, there will be a point where it's like, it's going to be way more efficient to be in person with a lab TA when you get stuck. So feel free, if you're in lab section 1, come any of the other lab section times to be able to get in-person help. And then anybody who is wanting extra help, wanting to attend that lab section that's virtual, feel free to also do that.
And then our first lab sections will be next week. It will be short, probably a half hour. You're going to go meet your TA, make sure you know where the classroom is, and about how we're writing lab reports, is how the labs are graded here. So we'll talk a little bit about that. And then your first full lab will be the week of Labor Day. So it's a little dicey because there is one Monday lab section. So I wrote this all on Canvas, but that Monday lab section, I believe you can get the first lab done. We run 4 labs over the term. Each one takes 3 weeks. So I believe you can get your first lab done in 2 weeks fine. And so you can just go the second and third week. We'll also offer to let you sit in a different lab section that week of Labor Day for those who had Monday lab, if you do want all 3 weeks.
Any questions about the lab? So there will be like a parts kit that you can go buy also from the
Ooh.
stock room. Oh, no.
So there is, yes, there is one with parts for anybody there's parts for lab 1 there for the paperclip launcher. If you're doing the paperclip launcher at home, I think some of the other parts are in this other lab kit, which I'll talk about in a second. But you will, if you're working from home, have to come at some point and try the paperclip launcher in person, because we have these boards with the rest of the circuit built there.
It works much better in person. So.
So you will probably want to stop by sometime in your free time and check that out to use and try. But the other thing is the second lab kit for the second half of the class is kind of incomplete right now. I'm working with them to get the other parts for it. So just wait a week or two on ordering that, or like, don't order that one till lab 2 when you really need it, or just order individual parts.
Okay, so go get the lab 1
Yeah.
parts is all you need to get for
Yeah.
now. So this week, just to be ready, just go get lab 1 kit.
Sorry about that.
No, that's okay. And then just know you're gonna have to get others. So,
And you don't have to buy it as a kit. You can also just go buy individual parts if you want. There's no harm to that.
yeah, and you're gonna find that you'll already have some of the parts from 1245. So just get kind of what you need at this point. And then again, if you want to use your 82, you can use it. If not, we're gonna start teaching you how to use the lab equipment in there.
Yep.
So
And
we're moving back to that, which is
next
kinda
week
nice.
would be the perfect time to go get the first supplies you need while after your half-hour session in lab, since you'll have some extra time.
So no labs this week at all, and then just go to a short lab next week. All right, any questions about that? If any of you have any issues doing 2240 and 2245 at the same time, do come after class and just kind of talk to me about that. We're gonna do another lab intensive for spring. So we found for some people that's successful, but we did find that this time it was really difficult for students to get all the work done in that 1 week time. So do know it's very intense. You have to be there 8 to 5 p.m. Monday through Friday, living lab work. So some people I'm seeing like a no way at all. So yeah, for some of you, not a good thing. For a few of you, it may be a good fit. So if so, just come talk to me about your situation and we can make that happen. All right, any other questions about lab? Thank you. Okay. All right. Okay, so we've gone through syllabus, the book. You understand the schedule. There is a schedule there, syllabus. I think if there's anything else you need to know. My contact info, so email is great. I do have to warn you, especially at the beginning of the semester, I just went through like 1,000 emails. So I get a ton of emails, so I do not mind answering email, but if I do happen to overlook it, just know that I was not intentional. Resend the email, like I'm just checking on following up on this, can you, have you gotten this if I haven't responded in a couple days. So if you haven't heard or it's more urgent, put urgent in the line. And I do typically get through all those emails, just sometimes it takes me a little bit longer because I get a mass amount of emails. You can also try and call me. If I am not available, just leave me a message and then I can try and call you back. The other way of meeting with me is office hours, and I do by schedule. I will be in my office typically right after class on Monday and Wednesday. This week, I won't be there Wednesday. I'll be there all after class today for walk-in hours, also for advising. So if you need any help with advising, I do that at the same time. So you can schedule a one-on-one appointment or you can stop in right after class at any time. Just feel free to schedule that. All right. Any other questions? As I said, no late assignments, and then submitting the assignments is pretty much all of it will be done on Canvas. Okay. All right. Grading accommodations. Okay, so I think that covers all of the syllabus logistics. Okay, so the format of, like I said, the style of what I have here is that we're going to work through the modules. And so I suggest going through this course introduction. There's a little bit more about myself in there, and then what resources there are. And then this is the first assignment, is tell me about yourself. And then you're going to see for each unit, there's going to be this overview and instructions. It's going to kind of outline what the objectives are, and then it will go through a list of these are the assignments for this unit. So I've color coded them per week so that hopefully that looks a little bit more organized. And then there's going to be a lot of learning material. So on the learning material, there'll be each of these topics. These are going to be a lot of your review. So here, there is some here already for that, but I don't have the RC and the RL learning topics up yet, but I will by later today. So there will be material that you can come in here, and for this first one, it's going to be based on your backgrounds are all different. So what do you need to review? And that resource material will hopefully be there for you. If you're finding something that is not here, just let me know and I'd be happy to include it. Because if you are finding, if there's math topics or other topics that you would like to have more resources on, I'm happy to supply those too, because if you don't feel like you remember that as much, other people probably are not. So I'd be happy to include those. So just reach out to me and let me know. And then there'll typically be some additional examples. There typically will be like, on some of these, there's going to be written examples and problem types that you'll see in the section itself, but then there might be the additional examples. So I try to provide you a lot of material to look through different examples to help you study and learn how to do these type of problems and kind of the differences between different problems. All right, any questions about how to look and find information on the Canvas course? Okay, also on these modules, well, I put a link here, let's see. So there's a link on the daily lecture content. So for the daily lecture content, I have notes that I typically work off of. So you'll want to get those. If you have electronic, you can just open them up, and if you write on those, there'll be a PDF, so you can download those and write on those. And then if you like physical, I would suggest printing those out before you come so that you have those to write on for each lecture. So there is one today. So you can either click on that link or you can find it under modules. There is this handouts and lectures. As you saw, I was, if you need to also attend, if you are even a little bit sick, I do encourage you to attend remotely so that we don't get everybody else sick. So I will put those videos from the Zoom. I will try and get those posted in here. So after the class, those will be posted. And then I have these handouts here for the lecture material. So this is going to be the one we're going to do today. If you have electronic notes and want to go to this and actually download those for today, feel free to grab those. And that's what we're going to go off of for today, is these lecture notes. All right, any question about where to find these lecture notes? A minute, as I see several of you are downloading those. Okay. So first review is about capacitors. Anybody remember, like, who can tell me what they think of when they think of a capacitor? What does a capacitor do?
I know this is the wrong way to think about, not wrong, but battery pretty much.
Yep, that's great. That's what I think of too, is think of it as like, okay, it's a storage of voltage, so a battery. So I can think of like, okay, I can charge up this battery and I can discharge this battery. So that is a great example. I like to think of it as a battery. So it is two parallel plates that get charged up with charge, and then they can stay there. And then so say I have a capacitor and I hook it up to a battery, it's going to start to charge up to that battery voltage. So if it's a 9-volt battery and I directly connect it, it's going to charge up. If you remember, it doesn't charge instantaneously. So it's not like, oh, okay, all of a sudden it's 9 volts. It's an exponential curve of charging. And it takes, anybody remember how long it takes to charge up to where we consider it to be almost charged? Anybody remember that? Okay, so it is called a time constant. And a time constant was tau, was the name of it. And it is about 63% of a full charge. So 9 volts would be the time, say that it is almost charged, would be 63% of 9 volts. So that would be what we call the time constant. So time constant is a number, and that is how long it takes to charge up to 63%. So if our time constant was one second, it would be like, okay, I'm going to charge up in 1 second to 63% of 9 volts. That is what we use for the time constant. So that tells us how fast and how fast it would charge or to discharge, same idea. So that time constant is a great number to understand so that we know how long does it take to how long does it take to charge and how long does it take to discharge. So if I had a time constant that was 10 seconds, would that be fast or slow? That would be slow. So we want it to be a low number to be fast. Does that make sense? Okay. So sorry, trying to get my notes. Okay, there we go. All right, so kind of this battery you're going to think of as so it's going to store charge. And this just goes through and okay, so the other thing about capacitors is that your current that goes through it is a change in charge over time. So that's why, again, it can't like instantaneously change because it's a description of how much charge is there over time. So when there's no change and you have it settled and it's been sitting there for a long time, that means your current goes to 0. So what does that mean? If you have I is 0, what does that look like? An open or a closed circuit? So an open circuit. So remember, current goes through an open. If you have 2 wires, it can't go through that. So it looks like the same thing as current is 0. So we're going to use that to help model what this does after it's been sitting for a long time. So initially, once I take like a capacitor out of a drawer, hook it up to a battery, initially it's going to start to charge up, right, in that exponential way. And then it's going to come up to 9 volts if I hooked it up to that 9-volt battery, and then it's going to stay at 9 volts until I make some other change. So when it's sitting there at 9 volts, it looks like an open circuit. Does that make sense? Seeing some nods. Think about that. So here's our tau. So this is our time constant. So we use 63% is considered, once it's almost to 63% of whatever value it's going to end up with, that's considered our, we're kind of there. So that's something you have to memorize, that it's 63% is considered there. Okay, so those are the charging and discharging curves that you see here. And then the use of capacitors, if you remember, is kind of like you store up some charge and then you want to discharge it. So the flash on a camera is a capacitor. So that is what is used to actually create that charge. It's used to stabilize power, high pass filter to filter. And so you can filter out low noise or you can filter out high frequencies. You can use it to create a differentiator or an integrator. So if you're trying to create a mathematical expression, then you would be able to use these two components to integrate it and differentiate it. All right, inductors. Anybody have an idea like how you describe inductors? Did you want?
Sure. Inductors is essentially just a wire where electrons are slowed down.
Okay. Okay, so if it's doing something to the charge, you can think of it as current, right? Because current is based off of charge. So I tend to look at inductors are a little bit harder to, to conceptually remember. Like a battery is easy, like, okay, here's a physical battery, but an inductor is a little bit more of a concept where it is like a current source. So if you think about it, it's changing the charge because of the wires that are wrapped around it. It creates this electromagnetic field, which changes your charge. So I like to think of it as a current storage instead of a voltage storage. And so it acts like a current source. So this one, instead of stores voltage, it's going to store current. So I like to think of it as a current source. All right, and then because it's changing, so it's L the IDT is the inductor equation. The voltage across it is L the IDT. Then, sorry. So now when you have no change, what happens here? So after it's been sitting for a long time, you're going to have no change. That means the IDT will go to 0. What happens? Yep. So DIDT will go to 0. And that means that your voltage is 0, which looks like a wire. Okay. So this is how you know, like after it's been sitting there a while, how am I going to model this component? All right, so same idea with the charging discharge. So it charges and discharges exponentially, just like the other time-dependent element of a capacitor. And the same thing is that time constant is going to tell you, again, at what percentage? 63%, good. Once it's 63% of final value, that's where we consider the time has been reached by that time constant. So if it's 1 second, it means it takes 1 second to reach whatever that final value is. So again, memorize 63% to know that that's what our definition of what a time constant is. Okay, so how do we use inductors? So one way that you guys have seen some of these buses that have the wave on them that go around campus. So those buses are actually using inductors and they're helping transfer power from as it's a big charging pad that's in the cement where they stop for their shuttle services. And so that's where they're actually getting charged, is on those. And so it uses inductive coupling to be able to transfer that energy and power. So it charges up a battery on the Wave buses. So, and Wave is actually a company. So they're interested in some of our students. We have a couple senior students that are actually working with them. So if you have interest in that area, there are some job opportunities there too. All right. So any questions? That's kind of just basically the quick review about capacitors and inductors. And now we're going to kind of go on to looking at them in a circuit. So if I have a simple voltage and resistor, where it's some circuit that I've lumped up into a Thevenin. Do you guys remember what Thevenins are? What's a Thevenin circuit?
I think it's just like a combined voltage and the whole circuit.
Voltage and?
Resistance.
Correct. So it's both a voltage and resistance, and that is some complicated circuit that I've reduced down to those two simpler elements. So it can be a really complicated circuit reduced to these two. So the VTH and RTH represents that more complicated circuit. So if I do that and connect up, just let me do the inductor first. An inductor. I want to know, like, okay, how am I going to solve this? So I have current going through this. How do I label the current? Which side is positive and which side's negative? Opposite. So arrow side's always the negative. So this is called that passive sign convention. And so just memorize that the arrow side is the negative side. So if this is the current going in this direction, there's no branches. So I've got to follow the current in the same direction. So that means that the current's going to go down also in this direction. So which side's positive? Top or bottom? Top will be positive and negative. So now if I do a voltage loop, I need to go through in a circle and go from wherever I start. I usually take this sign as I go through it. So if I start here and I kind of go around in this direction, I go and I physically circle the signs so that I remember which sign is correct. So I will circle all of those as I go around in a loop. This helps me to keep the signs correctly in this. And I see, like, okay, it's always that second sign that I go through. Or if you like to take the first sign, just be consistent, whichever way you want to go through it. So then I write this voltage loop is going to be what? Go ahead. Yep, so the plus will be VTH. And then what do I write for the next component of RTH and IL? Correct, so Ohm's law, which is IL RTH for that voltage. And now what do I write here though? So we know that the inductor L, we know the voltage across it, VL, is equal to L di dt. So this again is something you have to memorize, just like Ohm's law. So the component for L is going to be the voltage across it is L di dt, so I can use that. So L di dt. And then that's my loop. So I have now it's called a single order differential equation. And so I am going to rearrange this. I'm going to take the L over to the other side. So that becomes a positive. And then I leave these two components. And this is IL of T. Because we're talking about the current is changing over time. So we want to write the equation for IL of T is what our end goal is. So we want to write this in terms of IL of T. So now I'm going to try to, I'm going to do what's called separation of variables. And so I know that I see that I have the di dt and the IL of T. So I'm going to combine those together. So that is going to bring me to have di of T. Well, I'll do this step. So then I'm going to divide by L first. And now I'm going to take the T and I'm going to divide this by IL of T. So I can take out a negative here. And this will be a minus VTH plus IL of T. And so I can leave on that side, it's going to be a minus 1 over L. And sorry, this is dt on the bottom. So I now combine on the left the i's. And I can actually just take this and move it over to the other side. So I have on one side the di and on the other the dt. And all of the I components on the left, and now I can integrate to get rid of the differentiation. And this is going to go from T0 as like an initial value. And over here, it would be from time T0 to some other time T. And recall that when you have a du, au plus b, that integration is 1 over a natural log of the absolute value of au plus b plus some constant. So you can see here that that's that same form. So what is the integration of the di dt over that? What's that going to be? So A is what here? So U is going to be the IL. So this is U is the IL. What's this one? So this will be my A, right? And then this will be my B. So 1 over A will be 1 over RTH. And then natural log of this, which will be RTH IL minus VTH. And then it's going to be evaluated. So instead of the C, I'm going to evaluate it from T0 to T. So this part is going to be 1 over RTH natural log of the RTH IL of T minus VTH minus the natural log of RTH IL of T0 minus VTH. And so that is this side here. And now integrating the other side. Do you remember what 1 over L is? Integration? Anybody remember that? Close, it's actually E, or sorry, there's no T in there, right? So it's just gonna be minus 1 over LT. And evaluate T from T0 to T. Right, because there's no equation. L is just gonna be some constant. So this whole thing is going to be equal to minus 1 over L, and then that's just T minus T0. So how do I get rid of the natural log? I think I'm hearing it, yes. So you're going to raise it to the E, so taking an E of all of that. So that means it's going to be E raised to, well, I'm going to remove this constant over here and multiply it over to the other side. So it's RTH over L. And then I'm going to raise both sides to the E. So that will remove the natural log on the left. So this becomes an RTH IL of T minus VTH. Actually, let me do one more thing. Recall for natural logs. So another recall. When you have natural log of A minus natural log of B, that's the same as natural log A over B. So I can rewrite this in terms of a natural log A over B. And so that is going to look like this. And so if I have E raised to that, and then this is E raised to the minus RTH over L, T minus T0. And so now these will cancel out here. So I have RTH by L of T minus TH. And I can multiply this to the other side, so that becomes RTH ILT0. And that whole thing multiplied by E minus the RTH over L, T minus T0. And solving this then for IL of T. I'm going to bring the VTH over to the other side. So it's VTH plus all this. And then divide by RTH. So in this case, when we look back to the original, if this has been sitting for a long time, what happened to that inductor? It becomes a short circuit. And so what is the current I? It's just the current going through the resistor. So it's going to be Ohm's law. So sitting for a long time. So L becomes a wire, which means that IL, if I want to say infinite, is going to be just V over R. So looking at that VTH over RTH is kind of a final value. So I can look here and say, oh, this looks like my final value. This is my initial value. So that is the initial value of that current. Because T0 was the beginning value. Again, this is final value. And this looks like my tau. So if I have T over tau, tau is actually going to be, or 1 over tau, I should say. 1 over tau there. So if I just have any circuit and I combine them into a VTH and an RTH, then I can just use this general formula without having to do this every single time. So I now understand, hopefully you understand where this general formula came from, is all that derivation. And really the application part of this is just use that formula. So I would need to be able to figure out what is my final value what is my initial value, and what is my time constant. So if I can find all those, I can plug it into this formula that we just derived. So I now want you guys to break up into some small groups and go through the same derivation for the capacitor. So this is the, you guys are like, really? Yes, you can. So the capacitor circuit. So you have to memorize this equation for the capacitor is that the current IC is equal to C dV dt. So use that for the current going through it, which is also going to be the current going through the RTH. And then you're going to derive the expression for this one will be the voltage VC of T. So same step, you're going to create a current, label the currents, and write that voltage loop equation. And then try to follow the same steps that we did through the inductor for this. All right, so making sure everybody is getting the equation to start, correct? So you're gonna label IC kind of in here, and then this would be a plus. This again is gonna be plus minus here. And then the VC of T is gonna be a minus. So the equation would be plus VTH minus ICRTH minus VC of T equals 0. And then you're gonna plug in this IC here. So this is gonna be CdV of T dt RTH minus VC of T equals 0. And then you wanna combine the V's together on one side. And then try and go from the steps from there. Okay. All right, questions about how to get to this? Does that make more sense? I'm seeing a no. No, doesn't make sense. So he was mentioning, like, I'm getting confused because there's variables here. So what is my kind of unknown and what do I know? And that's a very good question. So RTH and VTH you have assumed have come from a big circuit. So they're going to be an actual value. So I would say that VTH and RTH are knowns and the capacitor value. So these would be known values. And then VC of T is my unknown. Does that help? Okay, so when you do look at these, I realize that that can be very confusing. So treat VTH, RTH, and C as like, if you want to even put in a number, feel free to put in a number, put in 10, 20 and 30, so you know there are differences between them.
And then you separate them, for example, VC depends on T.
So these would both be VC of T. So those are the same V.
Oh, yeah. So if we try and make the equation to the side EC0 to T, if that makes sense, and then I think you would just multiply the GT over that side. T0. Oh, and then we pull the same like that. But actually, we should already see over there. So then that will be So we don't get the R that we have C over here, and this will be 0, like this will be 0, of course, so that'll be that since Oh, no, yeah. But I got the signs. And it's just ordered out.
All right, if you want to kind of look through the work I've done to see kind of where, if you got stuck, where you got stuck. Take a minute to kind of go through this and see where your group was and kind of see if you did make an error, where was it? Or if you got stuck, please ask questions. Yeah. So DVC of T is the differential variable. So you're differentiating it on C of T. Yeah, so it is CDVC of T. DT, that's differential variables. So DV and DT are your differential variables. So you're solving for VC. And so when I combine them, the only way I can combine them, because they're separate quantities there, is to take the VC of T over to the other side and then divide by it. So that's the only way you can combine it to be in the same equation, right? Because they're adding. So the only way would be to divide by it. So you move that VCT over to the right side, and then you divide by it to get the quantity of DVC of T over. Does that answer your question?
Okay, so the left side is solid on the ECE, and the right side is not. But they're both the right side actually doesn't have any. So that's it's a small concentration. And the left side is all the ones that can't say the left side is all the ones that are close. So if they take the time to go that makes more sense. So it is like when you have the DV, you just don't have
All right, so looking at this, and now it's going to be very similar. If I look at this and think about it is, okay, it sat there for a really long time, what happens to the capacitor? Not short. Remember, it becomes an open because your current goes to 0. So that DI or dVdt becomes 0, which means your current becomes 0. So I said to memorize this, so you can always look at this to say, does it become an open or closed? By saying, okay, if there's no more change, this becomes 0, which means the IC will be 0. And that's how you know that it's open, because IC of 0 means an open. Okay, so don't necessarily have to remember that, but memorize the equation, and then you can look at that equation and say, okay, no more change. That means the dV of dt becomes 0, current is 0, open. So if it's open, what is the value for VC of t if it's open after it's been there for a long time? Yep, because there will be no current flow. Remember, if you have an open circuit, no current flows through that resistor. And so VC of infinite is going to be VTH. So this would be kind of my final value here. So looking at this equation, I see that this is a final value. And also here, final. This is the initial. And then tau here looks like RTH times C. So now again, I don't have to derive this every single time. Now that I've derived it once, I know where this all comes from that differential, first order differential equation. And if I go in and just find these values, I can actually write these equations for VC of T for the capacitor and IL of T for the inductor. So next time we're going to go through examples where we actually just now know how to do this derivation, and we can just look at, okay, let's simplify the circuit to just find these values, the initial value, the final value, and tau. And I can actually write a solution right away for these. Okay. So that will be what we're going to work on Wednesday. So we'll just continue on with these notes. And if you want to kind of review, this is going to be the step-by-step procedure that we kind of go through. Note that this T0 means initial value and T at infinity means final value. Okay, we'll see you guys on Wednesday.
Yeah.